right. So let's have our next speaker. So our next speaker is Jack Sisson from Bethel University, and his talk is tracking detector upgrades and monitoring for the CMS experiment. Jack, go ahead and take it away.
Yeah. Hello, everybody. I'm Jack, and I had the opportunity to work with a partner and Dr. Julie Hogan on doing some upgrades for the CMS experiment at CERN Large Hadron Collider. CERN CMS stands for the Compact Muon Solenoid, and that is a detector for collisions from the Large Hadron Collider. We were working on inner tracking detectors to map the trajectories of particles, and this inner ring of gold and dark gray, that is the tracking detector in the compact muon solenoid. The detector is currently not operational right now because we have a bunch of upgrades being prepared for around 2025. We're just trying to upgrade everything. So our main project this summer was to test the silicon microstrip sensors. Um, and these sensors are silicon wafers that look similar to this right here. And as they become depleted, they become very sensitive to charged particles. And as charged particles come off of the collisions, we use these sensors to make maps of the collisions. So these diodes right here and these strips of sensors right here is mainly what we were testing. And we were looking for the depletion voltage and leakage current. So this is our setup that we were using. We had a Keithley 2410 acting as a voltage source and an ammeter. We had an LCR to measure capacitance for the depletion voltage. We had an aluminum block that had a vacuum port to hold the silicon wafer in place and apply the high voltage. We had needles that connected back to the Keithley and acted as a ground source, so we could specifically check different parts on the wafer. And we had LabVIEW. We had LabVIEW controlling the whole setup, and LabVIEW made it automated so that we could run tests and change the voltage by just pressing one button. Our procedure was we would apply, or we would turn it, first we would take the silicon out and put it on the aluminum chuck. We would position it and then turn the vacuum on so that it wouldn't wiggle around as we were trying to place the needles down. We would use a microscope to position the needles on either the diodes or the strip sensors. And in this picture, you can see the microscope's view over here with the needle and the sensor. Then we had to cover the whole thing. Once we had the needles placed, we had to cover the wafer with a dark box, or because we were testing at current so low that even light would make a change in the data. So we had to get as little light as possible. That's why the lights are off in the picture. And then we would start a voltage ramp, and we would go from 0 to 500 volts in small steps of about 5 to 10 volts. And in the LabVIEW program, we had complete control over the range of voltages that we were testing and the steps of voltages. And as the voltage ramped up, we would sample the current or capacitance, depending on what we were testing at each voltage step. So for the depletion voltage, capacitance will flatten out when all the free charge is depleted. And as you can see here, it's very clear that we have a depletion voltage at around 100. The graph of 1 over capacitance squared shows the turnover very clearly. If we didn't use 1 over capacitance squared, it would be a little bit harder to tell, as you'd have the capacitance coming down from a high value and then flattening out. So this was just made it easier to see the depletion voltage. And we got expected results for depletion voltage. We were supposed to get around 100, and that's exactly what we got. And these tests really helped validate our LCR meter and its high voltage protection circuit. Before we started testing, we weren't exactly sure if our setup was going to work perfectly. So there was definitely some kinks we had to work out. And seeing these results definitely helped our confidence, you could say. Our second test was we were testing for leakage current. In the dark with no particle collisions, zero current is the expected moving through the silicon. Obviously, that's pretty self-explanatory, but we want no current to be running through the diodes if there are no collisions in the detector. But the leakage or the dark current increases slowly with voltage. And then eventually, once we've applied enough voltage to the silicon becomes so oversaturated with electrons that it just current flows a lot of current flows. And that's called the breakdown voltage. We were expecting a couple of nanoamps for our silicon, but we didn't get a lot of consistent results. As this graph shows, we have some diodes that would go up to very high current, but we had a couple that were pretty good. A lot of this was because the diodes weren't in the best shape. As this picture shows, we have some fraying down here, and previous tests can damage the silicon if the needles are placed incorrectly. And so we came up with a couple solutions. We added a picoamp meter to try and get less noisy current readings. We theorized that since the Keithley was sourcing high voltages up to 500 to 1000, and it was also trying to read these tiny currents, that it could be some internal noise from the high voltage. So we added a picoamp meter, which was a completely separate device. We designed and machined a new vacuum block. You can see down here the CAD diagram and the finished product. This got more aluminum to silicon contacts, so more voltage would be applied thoroughly, and it just had a more secure hold on the vacuum. We also added a dry airflow to control humidity. The humidity in the environment could affect the results, so we needed to get as dry air as possible in like the little black box that we covered it with. To add the picoamp meter, at first I tried to edit our program that we already had, but I decided it would be easier to just write an entirely new LabVIEW program, and you can see a screenshot of that over here on the right. And with all these improvements, we saw much better leakage current. As you can see, we have very small current and it flattens out. And then past 500, it breaks down, but that's not included. So then we transitioned into shifting for CMS. Now shifting is data quality monitoring for the CMS detector. As you know, the detector is currently shut down for operations, or for improvements, excuse me, but we can still shift recreations of past runs with new software and improvements, and those still need to be verified to make sure that they're valid data. So when the detector is up and running, they'll have shifters coming in per day, and they will just verify that the data coming off the detector is good. And we had to verify that each run was valid and see if any bad runs could be recovered. We learned a lot about the features of the data quality monitoring GUI. As you can see right here, it's a little sample of what it looked like, just a lot of graphs. And we learned about a lot of the malfunctions that can happen in a run and what to look for. And yeah. Then we moved on to adding graphs to the DQM GUI. And we did this by programming Python to rearrange calculated data into new graphs. We added graphs to show each detector's layers efficiency over time. As you can see here in these two graphs, these show the layers of the trackers, and the color is their efficiency, and the x-axis is as time moves on. We used a tool called Run the Matrix, and that just simulates a run and generates simulated data. This was very helpful because we can make changes to the code on our local machine and test our changes with Run the Matrix and make sure that we didn't have to upload it to their repositories without any errors. So this screenshot of code down here produced these two graphs, and as you can see, it's pretty simple. At least it looks pretty simple. They have a very powerful kind of graph creation interface, but it's very tough to know which methods you want to use to get your desired results. So we had to learn a lot about their different interfaces. And we've continued.
1 minute warning.
Huh?
1 minute.
Okay, thank you. Okay, we finalized development of tests. Okay, so we finished up prototyping the testing apparatus, and we got good tests on depletion current and leakage current. We accomplished validation of reprocessed 2016 data, did some shifting, and we worked to integrate some new changes for the DQM code. And it was overall a very successful summer, and we had a good time. All right, thank you so much.
All right, let's virtually thank our speaker. Thanks, Jack. We do have time, so this is why we do this. Yes, for one question here for Jack.
If nobody else has a question, my classic question is, so why would NASA be interested in either of these results or in people being able to do these kinds of experiments?
I think that NASA should be very interested in what's happening in the frontier of particle physics, because a lot of those discoveries can help NASA directly or indirectly by just like bringing on new technology.